In this lesson, we're going to be talking about similar figures. The success criteria is I can identify similar figures, and I can describe a similarity transformation between two similar figures. Dilations do not preserve length, so dilations are not rigid motions. A similarity transformation is a dilation or a sequence of dilations and rigid motions. So I'm going to go down here. Similar figures. Two figures are similar figures when one can be obtained from the other by a similarity transformation. Similar figures have the same shape, but not necessarily the same size. The triangles below are similar. You can see down here, corresponding angles of the similar figures are congruent. So angle A corresponds to angle D, and those angles are congruent. C and F, those angles are congruent. And E and B, those angles are congruent as well. Okay, and then the side lengths of similar figures are proportional. Okay, so that means that the ratio of, let's say, side AC to side AB is going to be the exact same as the ratio of side DF to side DE. So that's what the similar figures having proportional side lengths means. Okay, and remember this symbol right here, that just means congruent. For example 1, we're going to determine whether triangle ABC and triangle JKL are similar. Well, if you notice, this looks a whole lot like a dilation is happening here. So let's just check that, okay? Well, A is the ordered pair, 0, 3. B is 3, 3. And C is 3, 0. Okay, and then for JKL, J is the ordered pair 0, 6. K is 6, 6. And L is 6, 0. Notice all I have to do to get from triangle ABC to triangle JKL is multiply each component by a factor of 2. So this would give me a dilation. Okay. Another way we can check this is to see if our side lengths are proportional. Okay, the side between AB, okay, AB is 3 units, JK is 6 units, BC is 3 units, and KL is also 6 units. Okay, so that's the same ratio. Now, you haven't learned the Pythagorean theorem yet, but you will learn that this side length, all you have to do to get from this side length to this side length is multiply by 2 as well. So anyway, the easiest way to figure that out is to write down the ordered pairs and see if you can multiply each component by one thing, proving that this is a dilation, which we have in our scale factor, which I'll write down here. Scale factor equals 2. So anyway, triangle ABC is similar to triangle JKL. And now we're done. For example 2, the red figure is similar to the blue figure. Describe a similarity transformation between the figures. Okay? Now it doesn't tell us exactly which one is going to which one's the image and which one is the original figure. So I'm just going to say that we are getting from the blue figure to the red figure. Okay? But you could also describe a way to get from the red figure to the blue figure. Okay? Well, first I'm going to start with this, and since I know that this is similar, that means the corresponding angles are congruent, okay? And then the side lengths are proportional. So I can kind of tell that this angle right here that points up, okay, corresponds to this angle right here that points down, okay? And then this angle right here, this corresponds to this angle right here. And then this is a right angle, so this angle and this angle correspond. And then this obtuse angle corresponds with this obtuse angle. Okay, and I notice that the orientation of this is pointing up, and the orientation of this relative to this one is pointing down. Okay, and the last thing I notice is that this size is larger than this size. Okay, well, first thing I'm going to do is I'm going to reflect this thing in the x-axis. Notice if I reflect this, okay, I'm going to have this thing that's now pointing up point down. So I'm going to say reflect in the x-axis. Okay, so now I'm going to actually draw that shape. So if I reflect this in the x-axis, I'm just treating the x as my mirror. Okay, so everything that is the same distance up from the x-axis, I'm just going to have those points be the same distance down from the x-axis. All right, so now I have a point right here, point right here. And I'm going to draw my line segments. By the way, this is not the only correct first possible step. You could do multiple things first and still get to your intended target figure here. But this is just one way that we could do it. Anyway, now I want to do something about the size of this figure, okay? So notice that this side length is only 1 unit, but its corresponding side length is 2 units. Okay, so I can kind of easily tell that I'm going to need to dilate this with a scale factor of 2. Okay, if you notice here, this is 2 units, the corresponding one is 4 units. Okay, and we won't bother with the diagonals, but they will also need to be multiplied by a scale factor of 2. So anyway, the next thing I'm going to do is dilate with a scale factor of 2. All right. Well, remember, my assumed center of dilation is the origin unless we are told otherwise, which are not here. So all I need to do in this case is just multiply each of my components by 2. Okay, so this is the ordered pair 2, -1. So 2 times 2 is 4. Okay, and then -1 times 2 is -4. So that's going to be right here. Then over here, I have 4 and then -1. Well, 4 times 2 is 8, and then -1 times 2 is -2. And then over here, I have 2, -2. Okay, well, 2 times 2 is 4, and then -2 times 2 is -4. So it's right here. And last, I have 3, -3. Well, 3 times 2 is 6. -3 times 2 is -6, and that brings me right here. All right, so by first reflecting the blue figure in the x-axis and then dilating this with a scale factor of 2, you can see that now I have the red figure. Okay, so I've successfully described a series of similarity transformations between the two figures, and now I'm done with this one. In example 3, an artist draws a replica of a painting that is on a remaining piece of the Berlin Wall. The painting includes a red trapezoid. The shorter base of the similar trapezoid in the replica is 3.75 inches. What is the height of the trapezoid in the replica? Well, if you look at our two figures here, we know that they're similar, okay? So what I need to do to figure out my h is use the fact that similar figures have proportional side lengths. So notice that 3.75 inches corresponds to the 15 inches, okay? And then h corresponds to 12 inches. So what I'm going to do right now is write a proportion, okay? So what I'm going to do is just do 15 over 3.75 equals, and since I started with this shape, I'm going to start with this shape on my other fraction too. So 15 over 3.75 equals 12 over h. Okay, so I also could have written this as 15 over 12 equals, and since I started with this side, the top side length, then I have to start with this top side length over here, 3.75 over h. So either one of these proportions will work. I'm just going to solve this one because we wrote it down first, but it really doesn't matter which one you use. You just couldn't do like 15 over h equals 3.75 over 12 because those sides do not correspond and those shapes wouldn't correspond either. Anyway, I'm going to get back over to this. So the easiest way to solve a proportion like this, in my opinion, would be to cross multiply. So I'm just going to do that. If I cross multiply, I get 15h, because remember I'm just multiplying these things, 15 times h, and this is equal to 12 times 3.75. Well, I'm going to multiply this out, okay? So if I do 3.75 times 12, well, I get 0, 15, 7, bring down to 0, I just get 5, 7, 3, 0, 0, 5, 4, move the decimal 2 spaces, so that's just going to equal 45. So I get 15h equals 45. Now I'm going to divide by 15 on both sides. I get h is equal to 3. Okay, so if I look back up here, the question is just asking for the height of the trapezoid. Well, my unit here is inches, so I know that the height of the replica trapezoid is just going to be 3 inches. So h equals 3 inches. And now we're done with this one.